find that interesting. All right, so let's talk about these anti-derivatives here. The first one being secant of 6x times tangent of 6x times dx. The dx not really being that important. So when I look at this, I don't look at the 6x's. I'm thinking that I know, it looks interestingly screwed on here. Sorry, one second. I know that the antiderivative of secant of x, tangent of x, is secant of x plus c. This pen I should really stop using. It's really not good. I did order more new pens. They will come. I will actually be. I know I keep saying I need new pens. I'm actually going to get new pens. So hold your horses. I know it's a day of excitement. So I know that. So then I'm going to make a guess. My guess is that the antiderivative of secant of 6x times tangent of 6x is going to be secant of 6x. But it's not quite right. Because if we take the derivative of secant of 6x, we need to get secant of 6x times tangent of 6x, but we're going to get secant of 6x times tangent of 6x times the derivative of 6x, which is 6. We're off by a multiple of 6. So what do? We divide by 6, or multiply by 1/6. And that is the correct antiderivative, because if we took the derivative of this, right, the derivative of this is 1/6 times secant of 6x times tangent of 6x times 6. And those 6's end up canceling out. And the derivative is exactly the thing it needs to be for that to be the antiderivative. Generally, and I said this last time, I'm saying it again because it occurs a lot. When you're anti-differentiating something and you can see that the thing you're getting, if you took the derivative, you would end up multiplying by a constant. So the antiderivative, we have to divide by that constant. So for this next one, I know the derivative of e to the 5x is e to the 5x times 5. So when I anti-differentiate this, I'm going to get e to the 5x divided by 5. Or times 1/5. I'm going to say divided by 5. I'm usually going to write 1/5 because it's the same thing. Plus the antiderivative of cosine of x is sine of x. The antiderivative of cosine of some stuff is sine of that stuff. But if I were to take the derivative of this, I'd end up multiplying by 4. So I need to divide by 4 to account for it. And then I need to add on a c, because of course we need a plus c. This idea, which we'll roll back around to when we start talking about the methods of integration, or anti-differentiation, whatever you want to call it. We're going to use those words pretty interchangeably because they are thought of pretty interchangeably. We'll refer to this as what I like to call a mini U substitution, where you're doing a U sub, which I know we haven't talked about yet, but this is we're kind of skipping the U sub because it's just almost too easy to want to spend the time writing all the stuff. But we'll talk more about U substitution later on because that's one of the methods I would say we use the most when we're integrating functions, if they're not just easy to anti-differentiate right off the bat. Questions about this before we completely shift directions? Well, not completely. Somewhat. All right, so yeah, which way do I want to go first here? Yeah, there's kind of a choice. I'm going to make that choice. All right, so before we get into the area under the curve, we need a couple little pieces of information to help us do some things. Specifically, we need to talk about, this is in my way, is what I need to talk about for a second. Sorry, let me move this here just a little bit because it's like right in my face. Let's see, okay, looks all right. Cool. We need to talk about sigma notation, sigma or summation notation. And let's just do it by doing some examples. So let's say that we have the sum from, people use I, K, and J typically. I'm going to use, I don't know, K. Doesn't really matter. We can use I if you like, or J. Have your professors used this notation at all yet? Yes, I see some yes, some. What letter have they been using? Okay, awesome. But really, anything's fine. I'll probably go back and forth to show you different things. So let's say we have the sum from k equals 1 to 4 of 5 times k plus 3. So all this means is we're going to plug in the values of k starting at 1 and going up by each consecutive integer to the last value of 4. So I'm going to plug in k equals 1 and get 5 times 1 plus 3. And then I'm going to index up to the next integer and get 5 times 2 plus 3. I'm going to keep doing that. I'm going to get 5 times 3 plus 3. And then I'm going to get 5 times 4 plus 3. I'm going to stop there because this says start at k equals 1 and end when k gets to 4. And I don't really care what this equals. It's something, I don't know. I actually don't really care. But what I do care about is the fact that we can rearrange things. I can rewrite this as, well, these first terms, 5 times 1, 5 times 2, 5 times 3, 5 times 4. I'm going to break those off first and write them with the 5 factored out as 5 times 1 plus 2 plus 3 plus 4. And then the other terms, I have a 3 times 3 times 3 times 3. Sorry, I said times. I should have said plus. Apologies. I have a 3 plus 3 plus 3 plus 3. And what I want you to see is this can be re-expressed as 2 different summations. I can write this as 5 times the sum from I equals 1, from k equals 1 to 4 of k, plus the sum from k equals 1 to 4 of 3. This last part's a little bit weird, but if I'm going from k equals 1 to 4 of 3, when k equals 1, I get 3. Plus when k equals 2, I get 3. Plus when k equals 3, I get 3. Plus when k equals 4. Right? It's like a constant function where you plug in different values of x, you still get the same output no matter what you plug in for x or k. So the point here is that you can take a summation of some stuff and break it apart across addition or subtraction into multiple summations, and we can also factor out or pull out any constants in front. So more generally, if I have the sum from k equals 1 to n of some constant times a sub n plus b sub n, b sub k and a sub k, apologies. N is the n value, k is the thing that's changing. We can totally break this up as c times the sum from k equals 1 to n of a sub k plus the sum from k equals 1 to n b sub k. And it really could be plus or minus. You can break up summations across addition or subtraction, not across multiplication or division. Right? If you have a sum of a product, it's not equal to the product of the sums. Kind of like how when you take the derivative of a product, it's not equal to the product of the derivatives. You have to use the product rule. There's a similarly terrible rule here, but it's not worth getting into. So for example, if I wanted to say, I guess I'll try to number. I always try to number things, as you might be aware from last quarter. I usually fail to keep doing it, but we'll try. So let's say I have the sum from k equals 1 to 5 of 4k squared plus 2k. I can make it easier, debatably, writing it as 4 times the sum from k equals 1 to 5 of k squared plus 2 times the sum from k equals 1 to 5 of k. And then I could actually write it out. That's going to be 4 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. This pen's starting to go 2. Plus 2 times 1 plus 2 plus 3 plus 4 plus 5. And we could calculate that if we really wanted to. That's not really the point of actually. So this is equal to something. You find it on your own if you really care to, but it's not really important. So there's a few other things I want to talk about when it comes to these summation formulas. Specifically, I want to say 3 formulas. One we've already kind of talked about. I'm going to talk about it again. So if I have the sum from k equals 1 to 100 of the number 6, what am I going to get? Well, when k equals 1, I get 6. When k equals 2, I get 6. When k equals 3, I get 6. And I'm going to get 6 a lot of times. How many times? 100 times. That's going to be 100 times 6, which is just 600. I'm going to give you one more here because there's something that's a little bit tricky here that I want you to be aware of. I saw this on someone's homework and just want to make sure that everyone's cool with what's going to happen here. So let's say we go from k equals 15 to, I don't know, something annoying like 89 of 4. So when k equals 15, I get 4. When k equals 16, I get 4. When k equals 17, I get 4. All the way to when k equals 89. And now here's the harder question. How many 4s am I adding up? So that's close, but off by 1. So here's how I remind myself what's right. How many 6s did I add up here? Everybody. Right. What's 100 minus 1? Oh, I'm off by 1. So if I want to find the number by subtracting, I know that this is going to be the number when I subtract, but then I have to add 1 back. And that's the number of 4s we have here. So 89, so that's 90 minus 15, which is, I don't know, 75. So you've got 75 4s, which is equal to 300. So if you end up having to, you probably won't encounter something like this, but just in case you do, make sure you adjust for that 1, because there is, right, there's 1 more than you actually kind of count when you subtract. Like if you subtract 2 numbers, the number of numbers you've counted is 1 more than that. Yeah. So what's happening here, another way you could think of this, and actually this is kind of a useful thing as well. If you really wanted to, you could imagine this as the sum from k equals 1 to 89 of 4. So I'm adding up everything starting at k equals 1 all the way to 89, but then I don't actually want the first 14 of them, right? I really wanted to start at k equals 15. So I really want to subtract off the sum from k equals 14. Sorry, from k equals 1, apologies, to 14 of 4. Let me write it out a little bit more terribly here. This is going to be 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. This is going to be 89 times. So here's the first 14. Here's number 15. Here's number 89. So here's all 89 4s I get from this first part here. And then I'm going to subtract off these first 14. So I'm really only doing the 15 through 89. Which I wanted to write in a different way. I wanted to write minus the first 14 4s. That's why I'm doing that, because I don't want the first terms, because here, kind of atypically, I started at k equal to 15, not k equal to 1. Most of the summations we encounter in this section are going to start at k equals 1. But later on, especially when you take 21C, and you start doing series and sequences, you will have series and sequences that start at places other than k equals 1 or 0. Yeah.
So that one in the first one, it's still 100 because it'd be 100 minus 1. I mean, yeah, minus 1 plus 1.
Exactly. Yep. But it's easier to envision it that way, right? Because you know that if you start at 1, you're just going to get the number of things you count when you at whatever number you end at. So here we would, get that. All right, there's 2 other formulas I want you to be aware of because we typically use them. I will show you the derivation of one of them, which is easy. And then I'll refer you to a handout that I'm going to post on Canvas if you want to prove the other one. In fact, I definitely remember when I took 21B, my instructor made us prove these formulas to ourselves. So it's worth doing. The first one's kind of nice. So I want to find the sum from k equals 1 to n of k. So I'm just going to start adding up. I'm going to get 1, 2, 3, 4, plus all the way to n minus 2, plus n minus 1, plus the very last number, which is n, where n is some positive integer. Well, what does that add up to? N should be a finite positive integer, so it should not be infinity. If it was infinity, then we would get infinity, because you add up all the numbers from 1 to infinity, that's going to be infinitely large. Yes? To show what the terms before the last one. So for example, if I was doing a real number, the sum from say like k equals 1 to 40 would be 1, plus 2, plus 3, plus all the way to the last few numbers would be 38, plus 39, plus 40. So if n was 40, there's 40, and then n minus 1 is 40 minus 1, which is 39, and then n minus 2 is 40 minus 2, which is 38. This idea comes up also, but again, I'm gonna say in 21C, when you start looking at factorials, sometimes it's good to write down like the next term that's lesser than your starting term. So you have like some biggest term n, and then n minus 1 is the next smallest integer, and then n minus 2 is the next smallest integer, and so on and so on and so on. But how am I gonna figure out what this adds up to? Well, I'm going to employ some trickery. So I'm going to take this series, the summation, and add it to itself. But I'm going to change things up just a little bit. So I'm going to have the sum from k equals 1 to n of k plus the sum from k equals 1 to n of k. If I add those together, I'm going to get 2 times the sum from k equals 1 to n of k. Right? If you add something to itself, you just get double it. But then watch how I write this out. The first one's going to be 1 plus 2 plus 3 plus all the way to n minus 2 plus n minus 1 plus n. But for the second one, I'm going to flip the order that I write them out. I'm going to start at n instead of 1. So I'm going to do n plus n minus 1 plus n minus 2 plus all the way down to 3 plus 2 plus 1. And then we're going to add these together vertically. So check it out. 1 plus n, I'm going to write as n plus 1. 2 plus n minus 1, see, n minus 1 plus 2 is going to be n plus 1. What about 3 plus n minus 2? Oh, n plus 1. What about 3 plus n minus 2? I mean, same thing. And 2 plus n minus 1? And n plus 1? How many n plus 1s do I have? How many terms did I add up? N of them. So this is really equal to n times n plus 1. But then if I divide both sides by 2, I can say that the sum from k equals 1 to n of k is equal to 1 plus 2 plus 3 plus all the way to n. And that's equal to n times n plus 1 over 2. So just to go back here for a second, if you actually wanted to know what all the numbers from 1 to 40 added up to, you would say, okay, well, that's going to be equal to 40 is my n. That's going to be 40 times 40 plus 1 divided by 2, which ends up being 20 times 41, which is 820. Kind of cool. There are other ways of proving this formula, but this is kind of the fanciest way, I think. It's the funnest way of proving it, I think.
You said n plus 1 is a finite number?
Yes, n is a finite number.
You were saying the list can go on and on.
Right, it can go on and on, but you have to pick a stopping place. Now, the truth of the matter is we are going to use this formula to find the area under the curve, and to do that, we are going to take the limit of that expression as n goes to infinity. But we're going to deal with the n's before we kind of get there, so not to worry. The other formula, which we're not going to prove, I should say the other formulas we're not going to prove, are the following. The sum from k equals 1 to n of k squared. So if I add up all the squares, 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to n squared, and your teacher probably does want you to memorize this formula, it's equal to n times n plus 1 times 2n plus 1 divided by 6. I know it feels like that formula might be coming out of nowhere. I would encourage you to look at the thing I'm going to post on Canvas to kind of see where that comes from. It is a little bit challenging is not the right word. It's time consuming to prove. And I would not like to use our class time to do that. So look at Canvas. I'm happy to talk about it in office hours if you like, but we're going to leave that there. I will point out though, if you wanted to find, for example, the sum from k equals 1 to 20 of k squared, which is 1 squared plus 2 squared plus all the way to 20 squared, that's going to equal 20 times 21 times 41 divided by 6. And then you cancel a 2 here and a 2 here and a 3 here, and a 3 here, and get 10 times 7 times 41, which is something. I don't know, 2870, I think. Sounds about right. But that's not really the point. We don't really care what that is. We really care about this formula. We are going to use that formula to help us find the area under a curve. And I'm going to liken this to when in 21A, you spent some time finding derivatives using the limit definition of the derivative. And it was kind of awful, right? You had to write out all this long f of x plus h minus f of x over h, and then expand it out, cancel stuff, and then take the limit of that eventually. We're going to do the same sort of thing here, where we're going to have some mess of an expression that we're going to simplify and then take the limit of it to find the area. And then eventually, when we talk about the fundamental theorem of calculus, we're going to have the much easier way. We're going to have the power rule, but for antiderivatives, and all the other kind of nice derivative rules, but for antiderivatives, they're going to help us find the area under the curve in a much faster way, not using this limit definition process. But we have to walk before we can run, so we're going to do this part first. The other formula, and technically you can find formulas for any power of k, but we usually limit ourselves to k to the first, k to the second, k to the third. The sum from k equals 1 to n of k cubed, which is 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed. I think this formula is super cool. It's n times n plus 1 over 2 squared. Or in other words, which I think is just neat, if you add up all the cubes from 1 to n, or from 1 cubed to n cubed, it's the same as adding up all the integers, because that was the formula for the sum of the integers from 1 to n, and then squaring it. Which I just think, I don't know, it seems like such a large coincidence. You're like, that really works? Yeah. Check it out. 1 cubed plus 2 cubed plus 3 cubed is 1 plus 8 plus 27, which is 36. And 1 plus 2 plus 3 squared is 6 squared, which is 36. And go as far as you want. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 36 plus 4 cubed, which is 100. And yeah, 1 plus 2 plus 3 plus 4 squared, also 100. Kind of cool. I think it's really cool. I'm not gonna lie. Like, this is what I learned this. I was like, really? That works every time? Yeah, it works every time. Which is nice because it kind of means you don't have to memorize. There's one less thing you have to memorize, right? If you know that the sum from k equals 1 to n of k is equal to n times n plus 1 over 2, then this formula kind of comes along for free. If you just remember that, oh yeah, the sum of the cubes is just that formula squared. It's always good to memorize less things if you can get away with it. Yeah. Questions about this? Other than the question, can you prove that for me? Because I can, but I don't. So I'm going to ask you to believe this. And again, I would encourage you to look at the thing I'm going to post on Canvas if you're curious about how you would actually prove that the sum of k squared is equal to n times n plus 1 times 2 plus 1 over 6. It's not too hard to follow, but it does take a little bit of time. All right. Is that enough? Have I said all the things I want to say? Oh, there's one more thing. Sure. Yeah. One more thing you might want to be aware of. Now that I've said it, I'm going to do it anyway. So, telescoping sums. So here's an example of a telescoping sum. So the reason it's called, the thing that I'm about to do is called telescoping sum, is because if you like extend the telescope, you've got kind of all these things, I'm going to say not really, but added together. But then you can kind of squish it down to just kind of the first thing and the last thing, and all the other things kind of collapse on each other. That's why the thing I'm about to write is called a telescoping sum. So I'm going to find the sum from k equals 1, let's pick a real number, James, to 40 of k plus 1 cubed minus k cubed. If we start writing things out, I don't want to spend time simplifying anything because that's a bad move. It's gonna not help me. So I just plug in 1, I'm gonna get 2 cubed minus 1 cubed. Plug in 2, I'm gonna get 3 cubed minus 2 cubed. Plug in 3, I'm gonna get 4 cubed minus 3 cubed. Keep doing this for a while until I decide I've written enough terms. And then I do plus dot, dot, dot. And I'm gonna write the last 2 terms. So when k equals 39, I'm gonna get 40 cubed minus 39 cubed. And when k equals 40, I'm gonna get 41 cubed minus 40 cubed. And before I start trying to actually find all the cubes of these things, I'm gonna cancel some stuff. 2 cubed minus 2 cubed is 0. 3 cubed minus 3 cubed is 0. 4 cubed minus 4 cubed is 0. 5 cubed minus the 5 cubed that I didn't write down is 0. 39 cubed minus 39 cubed is 0. 40 cubed minus 40 cubed is 0. And I'm left with -1 cubed plus 41 cubed. Or as I would write it, 41 cubed minus 1. Whatever that happens to be. A lot less terms, right? All the middle terms cancel each other out and collapse down to just these beginning and end terms subtracted together. This comes up a lot in 21C. But it also comes up in the proof of the formulas we were just talking about. I think that's all I actually need to say about these formulas.
Wait, how did they work? Like you multiply negative.
I didn't multiply anything.
So
So I plugged it. So right here, this is when k equals 1. This is when k equals 2, k equals 3, k equals 4, k equals 39, k equals 40.
so where is the wait? So you plugged k. So where is the k cube? You have k plus 1 cubed.
Right.
And then
And so if
minus
k is 1, 1 plus 1 cubed is 2 cubed. And k cubed is 1
Oh.
cubed. If k is 2, 2 plus 1 cubed is 3 cubed, and 2 cubed is 2 cubed. And so on and so on and so on. Good. All right. So yeah, question. Sure. So this is positive 8, that's negative 8. They add to 0. This is positive 27. Sorry, let me point better here. This is negative 27. They add to 0. Positive 64, negative 64. So when I see a positive and a negative of the same thing, I know they're going to cancel out. You're welcome. I thought there's something else I wanted to write here, but I guess not. So yeah, let me go over here. Sorry, there's something I'm missing here, but I can see. That's fine. See that. Okay, so let's talk about finding area under. They don't want to. Yeah, and I keep wanting to use this blue pen, but I really shouldn't. Okay, leave the blue pens over there. So we're going to start by estimating the area under a curve. So let's estimate the area under f of x equal to the square root of x on the interval from 0 to 16 using n equal to 4 intervals or subintervals. I always go back and forth between calling them intervals and subintervals. I suppose subintervals is the correct term I should be using. This is the entire interval from 0 to 16, and I want 4 subintervals of equal width. Although they don't have to be equal width, we often choose to use equal width. Let's draw a picture. Oh, sorry, and one more thing. So, and then we're going to do this a few times. So in part A here, we're going to use right endpoints. All right, so let's see what we get here. from a picture. Here's my, oops, that's not perfectly straight, that's fine. So here's my f of x equal to the square root of x. I'm going from 0 to 16. I'm gonna break this up into 4 equal subintervals. So my delta x, which is the width of each subinterval. Again, this is assuming that you're using equal width subintervals, which might not always be the case, is going to be the entire length of your interval, 16 minus 0, divided by the number of subintervals, which in this case ends up being 4. More generally, your delta x is going to be equal to b minus a over n, where that's your a, your left endpoint of your interval, and b is your right endpoint. So I'm going to break this up into 4 subintervals. And when I'm breaking something up into, and if I'm trying to draw a picture, I have found the easiest way to break something up into a power of 2 intervals, so like 4 or 8 or 16, is to just cut things in half until you're done. Meaning cut the interval in half, and then cut each of those in half. Oh, look, I got 4 fairly equal subintervals, or at least fairly equal looking subintervals. And they're each going to be a width of 4 apart. So my next endpoint is 4. My next endpoint is 8. My next endpoint is 12. And my last endpoint is 16. The labeling here is important. I can't use this blue pen. Here. The leftmost endpoint is always going to be x sub 0. The rightmost endpoint is always going to be x sub n, which in this case is x sub 4. And then we just index up. This is x1, x2, and x3. If I want to use right endpoints to estimate the area under these curves, what that means is for my first subinterval, I'm going to pick the rightmost endpoint and use that point to find the height of the function. And then I'm going to draw a rectangle with that base and that height. Notably, an overestimate. Same deal for the second subinterval. I'm going to use the right endpoint, find the height, draw the rectangle. Same deal here, find the right endpoint, draw the rectangle. With the third subinterval. For the fourth subinterval, I'm going to find the height, draw the rectangle. And something I will point out is that if I'm using right endpoints to estimate the area under the curve, the endpoint I'm using for whatever subinterval I'm at has the same number as that subinterval. So for the first subinterval, I'm using x sub 1 as the endpoint. For the second, I'm using x sub 2. For the third, x sub 3. For the fourth, x sub 4. And that's always going to be the case if you're using right endpoints. So now if I want to estimate the area, I'm going to say that the area is approximately what I like to label as R4. R for right endpoints, 4 for the number of subintervals. And all this is going to be is the area of the rectangles. Why we use rectangles is they're easy to find the area. That's just going to be a base times the height plus a base times the height plus a base times the height plus a base times the height. So in this case, that's going to be a base of 4 times f of 4. And since they all have the same base, I might as well just factor out the base of 4. So let's write 4 times f of 4 plus f of 8 plus f of 12 plus f of 16, which is equal to 4 times the square root of 4 plus the square root of 8 plus the square root of 12 plus the square root of 16. And if you use a calculator, that ends up being approximately, oh, what was the value there? 49.17. Cool. Definitely an overestimate. You can see that the area under rectangles is obviously more than the area under the actual curve. Something I would like to point out is that that tool I was showing you last class could actually do the same calculation if you wanted to check that out. I would like to check it out because I think it's worthwhile. Let's look at this for just a moment. Oh, maybe. Sorry, why? Sometimes my controls are in the way. There we go. Can I get that over there? Maybe. Nope. Oh, Jesus, holy smokes. Sorry. It's always hard to go the right way. There we go. Okay, good. Let's make that big. And then I'm going to change the function to the square root of x. I hope. Let's find out if that works. It does. And then I'm going to change my interval from 0 to 16. And to zoom out, not in, out. I'm sorry. So this is, oh my goodness. There we go. Zoom in. Get closer to 16. Maybe you guys are like, James, just stop playing. No, I want to play around with it. It's fun. It is kind of neat. But what I really want to show you is you can actually verify what you've got here. So there we are, 16. I want to use right endpoint, which I'm already on. I could use left. That means right. And then I want n equal to 4. Which is hard to get to. So then if we zoom back out, look at that. There's our estimate. And look at the value there, 49.17. Kind of cool. And then really easily, we could slide this over to the left. And there's your estimate using left endpoints, which is the same idea. In fact, let's write it down here. But I will point out that it is 33.17. If we wanted to use left endpoints, oops, that's not what I meant to do. Sorry. Do that. Cool. So it gets a little bit tedious to draw this picture, so I don't want you to have to draw it a whole lot. In fact, I'm going to draw it again on here real quick. Here's what I'm going to do using left endpoints. So for this interval, for the first interval, I'm using the left endpoint to get the height, which feels kind of weird because your height's 0. For the second interval, there's my height. For the third interval, there's my height. For the fourth interval, there's my height. So these blue rectangles are giving you the area using left endpoints. And in this example, they're clearly an underestimate. I kind of want to talk a moment about how we write this. So I want to find the estimate using 4 subintervals with left endpoints. It's going to be, here's how I actually want to write this. Delta x, the base of each rectangle, or the width of each rectangle, times the left endpoints, or I should say really the function evaluated the left endpoints. So f of the first left endpoint is x0. The next left endpoint is x1. The next left endpoint is x2. And the last left endpoint is x3. Those are the 4 left endpoints of each subinterval. x0, x1, x2, x3. And then we could write it out. It's 4 times the square root of 0 plus the square root of 4 plus the square root of 8 plus the square root of 12, which is approximately 30, what was it, 33, I think? Double check. Maybe. Yeah, 33.17. Clearly a big gap between our left hand point estimate and our right hand point estimate. We would love to have a better estimate. How do we get a better estimate? Well, there's a number of good answers to that question. One thing you could do, anyone have a suggestion? Right, I can make the rectangle smaller by using more of them. And that's what we're actually going to do. But a couple other correct answers would also be to use the midpoints of each of these. That gives you a better estimate as well, typically, not always, but often. Or you could also average these 2 estimates to get a better estimate, which is not the same as using the midpoints, but often has a similar outcome to using the midpoints. But yeah, the real answer is, or the answer that we're going to employ is not midpoint, what you said, to use more. To get a better estimate, use more subintervals. So if we said, for example, I want to use n equal to 8 subintervals. Here's how that's gonna look. So we're gonna take this thing from 0 to 16. We're gonna break it up into 8 subintervals. Our delta x now is going to be 16 minus 0 divided by 8, which is 2. And our endpoints are going to be 0, 2, 4, 6, 8, 10, 12, 14, and 16. Similar labeling. This is x sub 0. There's x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, and the last one is x sub n, which is x sub 8. So if I want to use right endpoints, here are my rectangles. Every time, right, in each subinterval, I'm using the right side to find the height and then drawing the rectangle at that height. Again, it's going to be an overestimate. I should point out, using right endpoints doesn't always result in an overestimate. It will if your function's increasing. If your function is getting bigger from left to right, then the right endpoint is always going to be the highest value you could pick in a subinterval, and that's going to give you an overestimate. If your function was decreasing, then picking the right endpoints would give you an underestimate, and vice versa if you're using left endpoints. So here, our R8 is going to be our delta x times, that's just our base, which is 2, all the heights. So f of x1 plus, why am I writing all this out? I have a better notation for this. I should write this as the sum from k equals 1 to 8 of f of x sub k times delta x. That's a much more compact way of writing this. I don't really need that here though, because I know what all these things are. This is going to be 2 times the square root of 2 plus the square root of 4 plus the square root of 6 plus all the way to the square root of 14 plus the square root of 16, which ends up being approximately, how much is it end up being? Approximately 46.12. Which you would need to use, right? You would need to use a calculator, right, to actually get that approximation, or the tool on Canvas, or any number of ways of doing it. So great, our estimate, which is clearly an overestimate, is lower than the previous one, right? We got closer. We're zeroing in on the actual value. In a similar way, we can calculate L8. I don't really want to draw the picture. If I wanted to, I could see that L8 would be virtually the same thing, except it's going to be delta x. Let's write it the short way. It's going to be the sum from k equals 1 to 8 of f of not x sub k, which is the right endpoint, but x sub k minus 1, which is the left endpoint. Let's think about that for a second. If k equals 1, I get x sub 0. If k equals 2, I get x sub 1. If k equals 3, I get x sub 2. And if you go all the way to k equals 8, I get x sub 8 minus 1, which is 7. So I'm getting all the left endpoints, not the right ones. This is not the only way to write this, but it probably is the best way to write it at this moment. So this is going to end up being the square root of 0 plus the square root of 2 plus the square root of 4 plus all the way to the square root of 14 times our delta x. And just to make sure everyone's on the same page here, right? This is our f of x sub 0. That's our f of x sub 1. That's our f of x sub 2, all the way to f of x sub 7. And that ends up being some other number that's not all that important, but we're going to write it anyway. Approximately 38.12. So we have a better window for our area, right? Instead of the low of 33.17 to a high of 49.17, now we know that our area is between 38.12 and 46.12. Still kind of a big window, but this gives us the idea of what we're going to do. we're gonna keep letting n get larger and larger and larger until we get closer and closer to the actual value. In fact, if we look back at, can I do it? Maybe, maybe not. No, it doesn't want to show up. Fine. The cursor is my bane. We look back at that for a second. If you use either left or right endpoints, and then let the number of endpoints get larger and larger and larger, or the number of intervals get larger and larger and larger, your error gets smaller and smaller and smaller, and you get really, really close to the actual value. So it looks like the actual value there is pretty close to 43. I don't know if that's actually what it is. It might be actually what it is. But we'll see that later on, not today. Sure. So if we look at the first subinterval, for the first subinterval here, the left endpoint is x sub 0, and the right endpoint is x sub 1. So if we're using what kind of endpoints? What kind of endpoints are we using? Yeah, but which one specifically were you asking about? Right. So if we're using right endpoints, we have to start at the right endpoint of the first subinterval, which is x sub 1. No. It's each intervals or each subinterval's endpoints. And I'll say labeling these things helps. The way I always think about this is in each subinterval, the right endpoint has the same number as that subinterval. And the left endpoint has one less. So in an estimation using n subintervals, which I'm just going to draw very generically here. Here's some function. We're starting at some left endpoint. Let's use different colors, James, because I always make this mistake, making it look terrible. So we're starting at a left endpoint of A, which I'm going to call x sub 0, to a right endpoint of B, which is going to be x sub n. We break this up into n subintervals, so we've got all these subintervals. And if I start labeling the endpoints, well, that first one's x sub 0. Here's x sub 1, x sub 2, x sub 3, all the way to, well, actually, I'm going to hold off there for a second. This is the first subinterval. Here's the second. Here's the third. And you'll notice that for each subinterval, the right endpoint has the same number. So for this generic subinterval here, which is the kth subinterval, the right endpoint is x sub k, and the left endpoint is x sub k minus 1. And then finally, for the very last one, the nth subinterval, the right endpoint is x sub n, and the left endpoint is x sub n minus 1. Good. We're going to use that in just a second. For sure. Oh, yeah, that, sure. Wrong place. Okay, so the idea really is that we want to use this to find the actual area under a curve by taking the limit of all these areas as n goes to infinity. So let's look at an easy example, meaning a function that's not hard to find the area. Unlike the square root, which is kind of, although it can be done. So let's say that we want to find the area under f of x equal to 2x plus 1 on the interval from 1 to 3. Okay. Which we're going to write in the following way, which is expressed as the following definite integral. The integral from 1 to 3 of 2x plus 1 dx. There's a reason for this notation, which we will get into later on when we talk about the fundamental theorem of calculus. But for now, the way, no, sorry about the terrible, sorry, there. For now, when you see this, you should just think, okay, they're asking me to find the area under that curve between x equals 1 and x equals 3. we draw this, and I'm gonna draw it kind of exaggerated. Give myself a lot of horizontal room here. It's gonna look like this. Where here's x equal to 1. Here's x equal to 3. I'm trying to find the area under that curve. Fun fact, you can find the area under this curve without doing any crazy calculus. That's a trapezoid. Or as I would prefer to think of it, it's a rectangle and a triangle. If you draw this horizontal line here, you can see that I've got a rectangle whose base is 2 and whose height is however high the function is when I plug in 1. If I plug in 1, 2 times 1 plus 1 is 3. So the area of that rectangle is 2 times 3, which is 6. And the area of that triangle, well, this triangle here, the base is 2. And the height is, well, let's see, how high is it here? If I plug in 3, 2 times 3 plus 1 is 7. And the difference between 3 and 7 is 4. So the height there is 4. So the area of that triangle is 1/2 the base times the height. So adding those up, I get 6 plus 4, which is 10. There is a formula for the area of a trapezoid. You could know it, I guess, but I would prefer just to think of it as a rectangle triangle. Okay, so that's the easy way to do this, but now we're going to do it the hard way. And why are we going to do it the hard way? Well, not every function or every area under a curve is going to look like a rectangle and a triangle. There's going to be lots of things that are actually curvaceous that you can't just break up into nice polygons. So we're going to start with this easier one, and then we'll work on a harder one. So let's draw our little x sub i's. So this x sub 1, that's going to be our x sub 0. I should back up a little bit. Let's find our delta x. Our delta x is going to be b minus a over n, which in this case is 3 minus 1 over n, which is 2 over n. N is just n. It could be 5, it could be 1,000, it could be 1,000,000,000, but we're going to leave it as n because we're going to, at the end of this, take the limit as n goes to infinity to get the actual area, not just an approximation. Cool. So then this is x sub 1, x sub 2, x sub 3, all the way to some x sub k minus 1 and x sub k, and then all the way to some x sub n minus 1 and x sub n. So here's what we're going to do. We're going to write down the formula for the area of the rectangles. So here's my first rectangle. Here's my second rectangle. And I'm going to use right endpoints. Now your teacher, and I don't know what they've said, the teacher might have said something about using left endpoints or using any point in the interval with like an x sub I star. You can use any point, and here's why. What we're going to do is we're going to take the limit as n goes to infinity, or your teacher might say you're going to take the limit as the partition gets closer and closer to 0, which we'll come back to a little bit later on. But when we do that, each of the subintervals gets infinitesimally narrow. And so it doesn't, when something's really, really narrow, it doesn't matter if you pick the left endpoint or the right endpoint or some point in between them, because they're all getting smushed together and essentially picking the same point either way you look at it. So that's why we can pick any point, and we like to pick the right endpoint because it's the easiest to deal with. So let's see what we've got here. Our area without a limit is approximately, again, we're just adding up the areas of the rectangles. It's the first base times the height. Delta x times f of x1 plus delta x times f of x2 plus delta x times all the way to f of xn. But I do want to write this in a more compact way because it's going to get real tedious to write this out a bunch of times. So we're going to rewrite this as the sum from k equals 1 to n of f of x sub k times delta x. And then if we want to actually find the area, actually find area, we're gonna have that the area under the curve from A to B of f of x dx is gonna equal the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k delta x. This is one version of the limit definition of the integral. There are others, but this is the one we're going to use because it exists. All right, so in this particular case, we're going to say that the integral from 1 to 3 of 2x plus 1 dx is equal to the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k. We're going to figure out what that is in a second. But we're going to leave some space here. We're going to figure that out. Times our delta x, which we already know. We know that delta x is 2 over n. So what's our f of x sub k? Well, the thing that you're integrating, that function there called the integrand, that is your f of x. So f of x is the integrand. So that's essentially what's going to go here, except instead of plugging in x, we're going to plug in x sub k. So we have to find a formula for x sub k. It can be memorized, but I like to think about what it is before I just tell you what the formula is. So if we look back up here for a second, let's write some things down. X sub 0 is 1. X sub 1 is delta x to the right of 1. So it's 1 plus delta x. X sub 2 is 2 delta x's to the right of x sub 0. X sub 3 is, how many do you think it's going to be? How many delta x's from x sub 0 is it? It's going to be 1 plus 3 times delta x. I think we're seeing a pattern here. X sub 4 is going to be 1 plus 4 times delta x. All the way down to x sub k is going to equal 1 plus k times delta x. Which, if we plug in what delta x is, this is 1 plus k times 2 over n. Now, there's a nice check you can always do here to make sure you've got the right formula. We know from this picture, the x sub n should be what? X sub n is the right endpoint, the last right endpoint, which is 3. If you plug in n here, look what we get. I know I'm kind of squeezing things in. This is a bad habit of mine, trying to break it. X sub n is 1 plus n times 2 over n. But n times 2 over n is 2. 1 plus 2 is 3. That checks out. So if you plug in n for your subscript, you should end up with your final endpoint, which is 3 in this case. All right, so our f of x sub k, well, x sub k is 1 plus, I'm going to write this as, instead of k times 2 over n, 2k over n. And then our function f of x is 2x plus 1. So putting those together, f of x sub k is f of 1 plus 2k over n, which is 2 times 1 plus 2k over n plus 1. A little bit messy, but not the worst thing we've ever seen. So 2 times 1 plus 2k over n plus 1, all of that multiplied by 2 over n. Woo! All right. It's terrible the first time. It's terrible every time. It's the most terrible the first time when you're sussing it all out. After the first time, at least the process is a little bit more like, okay, I have an idea of what I'm doing. Still writing it all down and figuring it out it's terrible. It's always terrible. But it's manageable. So let's do it. Sure. So from the graph to here, what I did is I broke the area up under the curve that I'm trying to find into n subintervals. Each subinterval has a width of delta x equal to 2 over n.
Wait, so why there's like a gap between those areas?
Because I can't write all n of them. So I don't actually know what the number n is. So there's a bunch of things in here,
Okay, okay.
and there's a bunch of things in here. And then we found the endpoints. We said that x sub 1 was 1. So x sub 0 is 1. X sub 1 is 1 plus delta x. X sub 2 is 1 plus 2 delta x's.
Yeah.
All the way down to x sub k is 1 plus, well, we added delta x k times.
Yeah.
And then we said that the area under the curve is approximately just the area of the rectangles. So each rectangle is base times height, base times height, base times height, all the way to base times height. We compactified that, writing it in the sigma notation here. And then we said, well, that's the approximation. And then if we let n go to infinity, then we're going to get actually the area under the curve. So this is one way of defining the area under the curve, is that the area under the curve, f of x from a to b, is the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k times delta x, where delta x is b minus a over n, and x sub k, the formula for x sub k is always going to be a plus k times delta x. I never memorized that because it just doesn't stick in my head, but that is the formula. And
X sub k is
your left, so here our 1 is also called A, and our 3 is also called B. The left endpoint is 1, the rightmost endpoint is B. Sorry, the leftmost endpoint is A, rightmost endpoint is B.
and then x sub k is exactly
A plus k times delta x,
oh
which is A plus k times B minus A over n.
yeah
And if you look at this, it's kind of cool. If k is 0, then x sub 0 is a plus 0, which is just a. And if k is n, x sub n is a plus n times b minus a over n. The n's cancel, and a plus b minus a is b. So the x sub 0 really is a, and the x sub b, so the x sub n really is b, which is a nice way to check it out. And now we're just doing this for this particular example. We're saying, okay, we're trying to find the area under the curve 2x plus 1 from 1 to 3. And we're going to write that as the limit as n goes to infinity of the sum from k equals 1 to n of 2 times your x sub k plus 1, right? That's your f of x sub k times your delta x. And now we're going to do the algebra part, which is just multiplying it all out and using the formulas that we know. Which again is not particularly fun, but it is doable. So we're going to write this as the limit as n goes to infinity of the sum from k equals 1 to n. Yeah, we'll do that in a second. Before I do this, one quick thing I want to make sure everyone's cool with. If I said, what's the limit as n goes to infinity of 2n cubed plus 5n plus 1 over 9n cubed plus 4n squared minus 3, you would all tell me that the limit was what fraction? Right, 2 over 9. Because when you have a limit as your variable goes to infinity of a rational function, and the degree on top and the degree on the bottom match, the limit is always the quotient of the leading coefficients. And it doesn't matter if it's multiplied out or not. If I have the limit as n goes to infinity of, say, like n times 3n plus 5 times 2n minus 6 over 4n cubed plus 8, the highest power on the bottom is still 3. The highest power on the top, if I multiply that out, would still be 3. What's the coefficient of n cubed on the bottom? Everybody. Okay, harder question. What's the coefficient of n cubed on the top? Definitely. I hear people wanting to say 6, and it is. Because you have n times 3n times 2n, which is 6n cubed. But we're not going to multiply it out because we're lazy. We don't want to do that. It takes time. We don't need to do that. Cool. I'll come back in a minute. So then, actually not in this example, but we're gonna write this out as, let's see, we're gonna simplify this. I'm gonna distribute the 2 and get 2 plus 4k over n plus 1 still times 2 over n. I'm gonna write that as the limit as n goes to infinity of the sum from k equals 1 to n. 2 plus 1 is 3. 3 times 2 over n is 6 over n. And 4k over n times 2 over n is 8k over n squared. And at this point, when I've kind of multiplied it all out and gotten separate terms, there's something I always check for. You always want the power of n in your denominator to be 1 larger than the power of k in the corresponding numerator. So great, I have n squared and k to the first. Awesome. Here I have n to the first and k to the 0th. I'm good to go. Yeah, k to the 0th isn't a k, but it still works. So now we're going to use those summation things we talked about before. We're going to break this up into 2 pieces, right? As the limit as n goes to infinity of the sum from k equals 1 to n of 6 over n plus the sum from k equals 1 to n of 8. I'm going to write this as 8 over n squared times k. Because now what I want to do is pull out any constants. And you might be annoyed by what I'm going to say as a constant, but it is. As far as these summations are concerned, the only thing that is changing is k. Anything that's not k is a constant, including n. As far as this summation is concerned, n is just where you end. It could be 5 or 50 or a billion, but it's a constant number that's not changing until you take the limit out here, but that's after the sum. So as far as the sum's concerned, n is not changing. It's a constant. So I'm going to write this as 6 over n times the sum from k equals 1 to n of 1 plus 8 over n squared times the sum from k equals 1 to n of k. I feel like I'm just about to run out of the room right before I get to the end, but I think I can make it fit. But I'm going to try. I won't try too hard to make it fit. All right. If you add up 1 n times, what do you get? 1 plus 1 plus 1 plus 1 plus 1. You get n. So I've got 6 over n times n, which is just 6. You don't even have to deal with a limit there. Plus 8 over n squared times the sum from k equals 1 to n of k is n times n plus 1 over 2. Okay, so now that's going to be 6. And what's the limit as n goes to infinity of 8 times n plus 1 over n squared times 2? Well, on top, if I multiplied it out, my highest power would be n squared, and its coefficient would be 8. On the bottom, I have 2n squared. The highest powers are the same, meaning the limit's going to be the quotient of the coefficients, which is exactly 8 over 2, which ends up being 6 plus 4, which is 10. The same thing we said it was way back when, doing much less work. Terrible, but not impossible. But you might ask again, why would you do it when you could do it the easier way? Well, it's not always easy. Let's do another example because, yeah, we've got enough time. So let's do an example where you can't just know the area by using triangles and squares and circles. Not that we use a circle, but you could use a circle. So here is a very not terrible example. Let's find, how not terrible do I want it to be? I got 7 minutes. Let's make it really not terrible. We want to find the area under x squared from x equals 0 to x equals, let's go 3. 3, yeah, 3. Okay. And whenever I see something like this, I really should say, find this using the limit definition of the integral. Because if someone just said find that and didn't give you any instructions, after you learn the fundamental theorem of calculus, you should do it that way. You should never do it the long way unless someone tells you to do it. Okay, so we're going to write this as the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k times delta x. The delta x is the easier part to find. Delta x is going to be 3 minus 0 divided by n, which is just 3 over n. I really don't love memorizing the formula for x sub k. It's just maybe a personal bias. I don't know. I like writing it down and figuring it out. I like drawing my interval from 0 to 3 and breaking it up into n little subintervals. So there's x sub 0, x sub 1, x sub 2, x sub 3, x sub k minus 1, x sub k, x sub n minus 1, and x sub n. And so then I can say, okay, well, x sub 0 is 0, x sub 1 is 0 plus 3 over n, x sub 2 is 0 plus 3 over n twice. Okay, I see the pattern. X sub 3 is going to be 0 plus 3 over n times 3. And if I want x sub k, which is what I'm really looking for, it's going to be 0 plus 3 over n times k. If I want to check, I can go all the way to x sub n and say, oh, x sub n is going to be 0 plus 3 over n times n, but that's just 3 as it should be. I really like that check. I'm a big fan of plugging in n for k and making sure that I do get the upper value of my integral, which is the b value. I like that a lot. All right, so my x sub k is just 3k over n. So my f of x sub k, well, my function is x squared. So my f of x sub k is going to be 3k over n squared. My delta x is 3 over n. This one's actually a lot less ugly than the previous one because the numbers are and the interval is a little bit nicer. When you start at 0, the interval is typically a little bit nicer. You can probably make it all fit here without squeezing things in terribly. I'm going to multiply it out. I'm going to get the limit n goes to infinity of the sum from k equals 1. And let's see, 3 squared is 9. 9 times 3 is 27 times k squared divided by n squared times n, which is n cubed. Again, I see that I am in the place I want to be because my power of n is 1 larger than my power of k. Always what you're looking for, at least for these examples with polynomials. For other functions, we can't really do this, at least not reasonably. But when it's a polynomial, you always want your power of n to be 1 larger than your power of k. I'm going to factor out the constants like I did before. And the reason we do that is so that we can see the formula that we want to apply. And I should have given myself a little bit more room there. I'm going to factor out the 27 over n cubed in front of the summation. And I have the sum from k equals 1 to n of k squared. And we have a formula for that. The formula of for the sum of the first n squares, 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to n squared, that's just going to be or n times n plus 1 times 2n plus 1 over 6. So this whole piece right here is getting replaced by the thing that it's equal to, right there. And then it's the same sort of limit question we just dealt with. You don't really need to ask yourself what the highest power on the top of the bottom is going to be. If things are working correctly, they're going to be the same. I know that my highest power of n on the bottom is n cubed. I know it's also going to be n cubed on the top. So if I multiply out the bottom, well, the bottom's simple. It's just 6n cubed. So the denominator is going to be 6. And the coefficient of n cubed in the numerator would be what? You don't actually have to multiply it out. You just want to say what two things are multiplied together. Two times the 27 there. So 27 times 2. And actually, it's probably not in your interest to multiply it out because then you can just cancel some stuff and say 2 and 6 cancel, leave me a 3. 27 divided by 3 is 9. And just because I think it's worth you seeing the eventual connection that there's gonna be, and some of you probably have seen this before anyway. Eventually, what we're gonna do is we say, well, you don't have to do all this. The fundamental theorem of calculus tells us that instead of doing all this, we can instead find the antiderivative of the integrand and plug in the limits of integration and subtract the results. So alternatively, and again, we're a little bit a ways from there, but you'll probably be there next week. The thing that we're eventually leading up to is saying, oh, you can instead say that the integral from 0 to 3 of x squared dx is equal to the antiderivative of x squared, which is why we're spending time finding antiderivatives, because you have to be able to antidifferentiate the function to use the fundamental theorem of calculus. It's going to be x cubed divided by 3 evaluated between 0 and 3. We always plug in the top limit first, and we subtract and plug in the bottom limit second. And that's going to be 27 divided by 3 minus 0, which is also 9. So that's where we're going with all this. All right, stop talking. It's 4:29.